Welcome to the course on power quality. We will be discussing the numerical problems on improved power quality boost converter. Coming to the example 1, find the optimum value of the DC side inductor and DC link capacitor for a single switch power factor correction AC DC converter with the following specification. The rated power of 1000 watt, the output voltage 400 volt, the output voltage ripple less than 2% and the inductor current ripple less than 5%, the line frequency 50 Hz, supply voltage 230 volt, switching frequency 40 kHz under the continuous conduction mode, operation of the DC side inductor. This is the typical circuit with power control with the CCM and after designing and developing the model of control with the data, these are the waveforms, supply voltage, supply current, this is the inductor current and typically this is the DC link voltage and this is the capacitor current which is going into the capacitor, ripple current are going into that, and this is virtually the, you can call it the load current, and this is the output voltage like. So, based on this we have a now numerical part of this, given that the power is 1000 watt, output voltage 400 volt, supply voltage of 230 RMS with the 40 kilohertz design, supply frequency 50 hertz. So, input average will be 0.9 times Vs, that is 0.9 230, that is a 207 volt. So, we can find out the output load current, power divided by the output voltage, that is 1000 upon 400 2.5 ampere, from which we can find out the typically the duty cycle corresponding to that, average duty cycle 0.4825, and we can find out the input current, the output power divided by the voltage, average current input, the 4.83, and hence the optimum value of DC link capacitor we can find out from the standard relation which we derive I upon 2 omega. So, putting the value here we get this 493.3 microfarad, and the inductor calculation we can do from this formula which we derive V d into d f into this. So, putting the value it comes 10.34 millihenry. So, coming to second example, to find the value of the DC side inductor and the DC link capacitor for a switch single switch boost converter AC DC converter with following specification: the rated power of 150 watt, the output voltage 400 volt, the output ripple voltage less than 5% with the line frequency 50 hertz and 230 volt, and the maximum switching frequency 20 kilohertz under the boundary condition mode of the DC side. So, this is the typical circuit, supply voltage and supply current. Of course, this is before the MI field inductor current, and this is the capacitor current which is going to this capacitor, this is the load current, and you can call it the output voltage of 400 volt. So, coming to the calculation part, we are designing for output power 150 volt, 400 volt, ripple voltage of 0.05 per unit, the input supply voltage is 230 volt and 20 kilohertz of 50 hertz. So, equivalent output resistance is your V 0 I 0, it comes 1.06, and the output current is from power and voltage is 0.7, and we can have a average duty cycle. So, from this we can find out the value of the inductor, boundary condition inductor, once we know the output resistance and switching frequency and duty cycle. So, we get 3.43, and the design of capacitor corresponding to second harmonics, that we have a formula earlier. So, it comes 29.84 because of low power. Coming to third example, find the value of DC side inductor, DC link capacitor of single switch boost converter with the following specification: the rated power of 500 watt, the output voltage 400 volt, the output voltage ripple less than 5% and the frequency 50 hertz and the voltage 230 volt and switching frequency 20 kilohertz under discontinuous conduction DC side inductor. So, the supply voltage, supply current, and the inductor current, and then the capacitor current, the output voltage and output current like. So, given that output power 500 watt, 400 volt. So, we can find out the typically output current, then the equivalent output resistance, then the average duty cycle, and the for DCM we can find out the inductance 1.03. Hence, the DCM value of inductor should be less than this value. We can select even much lesser than that, and the output capacitor from this formula we get 99.47 microfarad. So, coming to another numerical example 4, calculate the value of output voltage ripple and the inductor current ripple for a single switch boost PFC converter with the following specification: rated power of 1000 watt, output voltage of 400 and DC side capacitor 1500 microfarad, and the boost inductor 5 millihenry, and the line frequency 50 hertz, supply voltage 230 volt and switching frequency 20 kilohertz and with the CCM operation. So, we have to calculate the performance from this. So, value are given, this is the boost converter with control, and this is typically the after putting the value and making the model of it, this is input voltage, input current, inductor current, capacitor current and the load current, DC load current, DC voltage. So, typically we get all these design, all the value are given of the specification these. So, we can find out the input current and the equivalent output resistance and output load current, then average duty cycle, then the capacitor. From this capacitor value we can find out the ripple 2.65 volt and percentage we can find out in terms of output, it comes only 0.66%, and the inductor output in typically the we can get, and from this relation of output inductor we can get a current ripple that come 1 ampere, as a percentage of this is only 20.7%. So, inductor ripple can be permitted even up to 25% or so. So, coming to a example of example number 5, find the optimum value of AC side inductor and DC side capacitor for bridgeless boost PFC converter with 2 switch boost converter with the following specification: rated power of 1000 watt, output voltage 380, output ripple 3%, input current ripple 4% and 50 hertz, supply voltage 230 volt and switching frequency 20 kilo. So, this is you can call it the bridgeless boost converter with the 2 switches. I mean we already discussed that one half cycle one operate, another half cycle another operate. So, with this specification of power 1000 watt, output voltage 380 volt with the voltage ripple of output 3%, current input current ripple 4%, the supply voltage 230 volt and switching frequency 20 kilohertz with switch supply frequency of 50 hertz. So, we can find out the average input voltage from this, we can find out the output load current from power divided by the output voltage 2.63 ampere, input average current 4.83, and we can find out the duty cycle from this comes 0.55, and the output capacitor we can find out from this typically from the ripple relation, putting the value it comes 367.36, and the input inductor current from this relation we can find out this comes 0.24 Henry, means typically 24 millihenry. Coming to this sixth example, calculate the value of the output voltage ripple and the input current ripple of 2 switch PFC boost converter with the following specification: rated power of 1000 watt, output voltage 400 volt and DC side capacitor 1500 microfarad and the boost inductor 5 millihenry and line frequency 50 hertz and supply voltage of 230 volt and switching frequency 20 kilohertz, and this is the typical circuit of your bridgeless boost converter. So, coming to the calculation, output power of 1000 watt, output voltage 400 volt, supply RMS input voltage 230 volt RMS, capacitor is given 1500 microfarad, inductor is given 5 millihenry and your switching frequency 20 kilohertz. So, we can find out average input. So, from we can from power and output voltage we can find out output load current 2.5 ampere, we can have input average current also, that is typically power divided by input voltage of 4.83 and output equivalent load resistance VO divided by 0, that is 160 ohm and average duty cycle, and we can find out the capacitor from this relation of second harmonic ripple, putting the value we can find out the ripple voltage 2.65 volt and taking as a percentage it comes 0.6631 and the input inductor virtually from this again the ripple current, can putting the value we can get a ripple current from here and then the percentage ripple will be 26.67. So, coming to the seventh numerical example, find the value of AC side inductor, DC link capacitor of 2 switch boost converter, bridgeless with the following specification: the rated power of 250 watt, output voltage of 400 volt and the output voltage ripple less than 5%, line frequency 50 hertz, the supply voltage 230 volt, maximum switching frequency 20 kilohertz under the boundary condition mode PCM on the DC side inductor for this bridgeless boost converter. So, from the given power of 250 watt, 400 volt, 20 kilohertz and 50 hertz frequency, we can find out the output load current and equivalent load resistance from V upon I 0 and then the duty cycle from input average voltage and the capacitance value from output voltage ripple, it comes 49.73 and the minimum inductance from this relation it comes 2.06 millihenry. We can select of course lesser than that for operating in DCM. So, coming to an example 8, a single phase bidirectional boost converter, half bridge also known as a voltage source converter, draws a 1000 watt from 230 volt 50 hertz mains, 4 is resistive load, the switching frequency is 20 kilohertz, AC inductor is 3 millihenry, power factor is corrected close to unity, modulation index and find it, determine the output DC voltage, the value of resistance of DC load, the AC mains current, the phase shift of fundamental component of pendulum voltage and AC supply current. So, this is the circuit of bidirectional boost converter. So, given here power, output power 1000 watt, supply voltage 230 volt, 50 hertz, power factor is maintain unity, the current inductor 3 millihenry and modulation factor 0.8 and switching frequency. So, from considering the power factor unity and input voltage and power, we can find out the input fundamental current 4.34. Then we can take inductor drop at inductance value at fundamental frequency, inductance is given. So, we can find out this is a, and then we can find out converter fundamental voltage VSA square plus inductor drop. It comes this one from this relation 230.06 and we get a fundamental inductor current drop, multiplying the reactance multiplied the input current. So, it comes 4.088 volt, and for the half bridge converter properly DC link voltage calculated from here. So, it comes 800 and resistance equivalent comes like from this voltage divided by this and the delta value from this relation of power flow when we get the typically 1.02 degree like. Now, coming to this full bridge converter, an example, a single phase voltage source converter, single phase voltage source converter based AC DC bridge converter, also known as a voltage source converter, is used in a solar power grid interface system with a power flow of 5000 watt and connected to 30 volt 50 hertz, the switching frequency 20 kilohertz and the AC inductor 2.5 millihenry. The power factor is corrected close to unity and maximum power, maximum PWM modulation index is 1 to operate in linear range. Determine the minimum input solar PV array voltage for power flow from DC solar array to the AC grid. The AC mains current, calculate the power angle between the grid voltage and the fundamental voltage of the voltage source converter and the grid current. This is the typical circuit. Here of course, we have a typically the PV. So, coming to the solution of this, we have a 5000 watt and 230 volt 50 hertz and power factor 1 and inductor is 2.5 millihenry, modulation 1 and switching frequency this. We can find out fundamental current from power and power factor unity with the supply voltage. So, it comes 21.739 ampere and reactance we can find out from fundamental frequency is given 2.5 millihenry. So, it comes reactance 0.785 ohm and from once we have a current and the reactance we can find out the inductor drop. So, excess into IS1 for fundamental voltage drop comes 17.065 and we can find out fundamental converter voltage VSC square VL1. So, putting the value of this and this is 230. So, we get 230.63 and DC link voltage we can find out from typically from this relation, we know modulation index and from converter voltage this comes 326.16 volt and the phase shift from this relation of power flow we can put the value and it comes 4.24 degree. Coming to 10th example, a single phase bidirectional boost PFC ACBG converter, also known voltage source converter, has a power flow of 4000 watt in either direction for battery energy storage system of 360 volt connected to the 230 volt 50 hertz mains and switching frequency of 20 kilohertz and AC inductor is 3.5 millihenry. The power factor is corrected to close to unity and converter is controlled in such a way that AC mains current is either phase out, either in phase or phase out from the AC mains voltage. Determine the modulation indices under the charging and discharging mode. At full power, calculate the power angle between the grid voltage and the fundamental voltage, voltage source converter and the grid current in both modes, charging and discharging. So, for the solution given that 4000 watt 230 volt 50 hertz and power factor 1 and VDC 360 volt. So, with this typical circuit, here we have a virtually the battery from which we are having a bidirectional power flow. So, we can find out the fundamental current, power divided by Vs cos theta, that is unity. So, it comes 17.39 ampere and the reactance at fundamental frequency 50 hertz. So, it is 2 pi f 314 into the inductor 3.5 millihenry to convert into Henry, it comes 1.099 ohm and the drop in the inductor fundamental voltage drop in the inductor reactance and the current fundamental current multiplied comes 19.11 and converter voltage, that is sum of your supply voltage square plus inductor voltage square. So, it comes 230.79 after putting the value typically this and 230 and the DC link voltage from this relation putting the value of converter voltage which we calculated and DC link voltage given. So, we can find out modulation is like 0.966 and phase shift in fundamental component of PWM voltage delta from this power flow relation, putting the value excess power, converter voltage and supply voltage, we can have this as a 4.75 degree. Coming to 12th example, design a single phase power factor corrected AC DC forward boost converter in continuous conduction mode with the high frequency transformer isolation operating at 50 kilohertz with the following specification, that input voltage varies from 100 to 140 volt RMS and nominal voltage of 120 volt 50 hertz and single phase AC supply and DC output 160 to 70 adjustable with the nominal voltage of 230 volt and 450 watt with the output voltage ripple of less than per. So, this is the typical circuit of this your forward boost converter, and going to the calculation of output voltage 160 to 70 and nominal voltage of 230 and input nominal 120. So, you can find out average input voltage corresponding to 90 and 126. So, we can find out from power given 450 watt. So, we can find out the output current 1.95 and resistance equal to 117.75 and input current 4.16, and from this relation we keeping a duty cycle we can get a turns ratio 1 and putting the value we get the typically duty cycle 1.5 and output voltage corresponding to 5.3 and the inductor for minimum maximum it comes 5.5 11.74 and capacitance value of 1.4 millifarad from second harmonic relation corresponding to that. Coming to the third numerical 13, design a single phase power factor corrected half bridge boost converter in discontinuous mode, so known as a voltage follower approach with a high frequency transformer isolation operating at 50 kilohertz with the following specification, input voltage of 100 to 140 RMS with the nominal voltage of 120 50 hertz, single phase AC supply, DC output is 160 to 70 and 230 volt and power output 200 watt, output less than percent. So, this is the you can call it half bridge boost converter because of this current fed we are putting boosting here. So, coming to the solution, that output voltage 170 to 160 to 270 volt, nominal output 230 and nominal input 120. So, we can find out the rectified output average voltage from diode rectifier, it comes like range 90 to 126 volt and then the power output 200 watt. So, from this we can find out output current means output power output voltage, that is fine, and equivalent resistance V open RO. So, it comes 264.5 ohm and the input average current P open input current. So, it comes 1.85 ohm. The output voltage given from the this relation V equal to V in N2 upon N1 into 2 1 minus T. So, it comes and hence the range of duty cycle 0.52 to 0.95. So, now to find out the turns ratio for duty cycle 0.95 for maximum output voltage of 270 volt and minimum voltage rectified voltage of 90. So, keeping the value turns ratio comes 1 and now put the value of minimum output voltage 160 and maximum rectified voltage. So, from this we can find out the duty cycle D equal to 0.6 which is greater than the minimum duty ratio, hence the turns ratio is 1 and from this we can find out the output voltage relation, we can find out duty cycle 0.7652 and the minimum inductance from this inductance form relation 145.8 microhenry, and the inductance value the capacitance value output capacitor will be equal to, putting the value it comes 622 microfarad. So, coming to 15th example, design a single phase power factor connected half bridge boost converter continuous conduction mode with the high frequency transformer isolation operating 50 kilowatt with the specification of 100 to 140 volt RMS, the nominal voltage of 120 volt 50 hertz, single phase AC supply and output DC voltage 160 to 270 volt, adjustable nominal voltage of 230 volt, output power 350 watt and output triple less than 2% like. And so, given here the output voltage 160 to 270, output nominal 230 and the nominal input voltage 120 and the rectified voltage is typically at the output is a 0.990 to 126 volt. So, the for a given power of 350 watt output current P upon V0 we get 1.521 watt ampere and input average current comes 3.24 and taking a output voltage relation from and duty cycle range typically 0.5 to 695. So, taking 0.95 the maximum voltage of 270 volt and the input voltage rectified is 90 volt. So, from this we can find out the turns ratio order of 1, and now the putting the value of maximum voltage pushed into maximum minimum output voltage with maximum input voltage, getting the turns ratio typically 0.6, which is greater than the minimum distance, and the turns ratio is taken 1, and from output voltage we can find out the duty cycle 0.7652, and the minimum inductance virtually from this relation we get 2.5 millihenry, and the inductance has to be less than this value to ensure the higher than this to ensure the, and the output capacitor corresponding from this relation comes 1.1 millifarad. Coming to another example, design a single phase power factor corrected push-pull boost converter in discontinuous mode of operation, also known as voltage follower approach, with the high frequency transformer isolation operating at 50 kilowatts with the following specification: 100 to 140 volt with a 120 nominal 50 hertz single phase AC supply, and DC voltage 160 to 270 volt with adjustable nominal voltage of 230 volt and output power of 1500 watt with output voltage less than 2% rebel. So, this is because of this inductor is a boost converter, and the voltage given output voltage is 160 to 270 to operate, and nominal output voltage 230 and nominal input voltage is 120. So, rectified output voltage from the diode rectifier will be 0.9 times 100, that is 90 to corresponding to maximum voltage of 140, it comes 126, and the output power for output power of 1500 watt, the output current is your P upon V 0, it comes 6.52 ampere, and the input current P upon V 0, it comes 13.22, and from the relation of output voltage we from duty cycle selection in the range of 0.5 to 95 and taking a 0.95 output and taking a minimum voltage of 90, we can find out the relation of turns ratio of 1, and then putting the minimum output voltage and maximum input voltage. So, we can find out the duty cycle, that is 0.6, which is greater than the minimum duty ratio, hence the turns ratio is taken 1, and from the relation of this input output with duty we can find out duty cycle 0.7652, and for design parameter the minimum inductance calculation from the this, so it comes 19.44 microhenry, hence the value of inductance will be less than this to ensure DCM, and output capacitor for second harmonic ripple, putting the value, it comes 4.67 millifarad. Another example, design a single phase power factor connector bridge boost converter in discontinuous mode of operation, also known as voltage follower, with the high frequency transformer isolation at 50 kilowatts with the specification of input voltage of 100 volt to 140 volt, 50 hertz single phase AC supply, and DC output voltage equal to 160 to 270 with adjustable voltage of 220 volt at 500 watt with output voltage less than 2. So, this is the bridge boost because of the inductor is operates as a boost converter. So, the voltage range output is 160 to 270, and the output nominal voltage 220 volt, and the input nominal is 120 volt. So, rectified output of diode rectifier is 0.9 input voltage, that is 90 volt for 100 input and 126 volt for 140 volt input, and then for a power of 500 watt the output current from P upon V 0 to 2.27 and input average current of 4.6296, and the ripple current corresponding to that will be 0. Because that is 5% of this typically this current. So, it comes 0.1135, and the output voltage range given from relation from V equal to 1 to 1. So, if you take a duty cycle range 0.55 to 95. So, now to find out the turns ratio of point D equal to 0.1 taken for maximum output voltage of 270 volt and minimum input voltage of 90, putting the value we get the turns ratio order of 1, and now for minimum input output voltage and maximum input voltage we get the duty cycle of 0.6, which is greater than the minimum duty, hence the turns ratio can be taken 1, and V equal to from this relation we get the duty cycle D equal to 0.75, and from the this relation for inductance minimum inductance calculation we get 58.40 microhenry, hence the value of inductance will be less than this value to ensure the DCM, and the output capacitor corresponding to ripple voltage relation, putting the value it comes 1.56 millifarad. So, coming to example 21, design a single phase power factor corrected bridge boost converter in continuous conduction mode with the high frequency transformer isolation operating at 50 kilowatts with the following specification: Pi equal to 120 volt, 50 hertz single phase AC supply, and output voltage 220 at power of 2.6 kilowatt with the output voltage ripple of 2%. So, this is the boost converter which is designed in typically in continuous conduction mode. So, coming to here output voltage ripple of 2% of 220 is say 4.4 volt, output power is 2600 watt and nominal output voltage of 220 volt and input nominal 120 volt, and typically the rectified output voltage will be 0.9 times 120. The output load current is P upon V 0, it comes 11.81 and input average current will be your 24.07 ampere. The output voltage from this relation from turns ratio, keeping the duty cycle in the range of 0.55 to 95. So, taking a for boost operation, so 0.95 and putting the value here, the turns ratio comes 0.2 and for duty cycle 0.55, the duty cycle is come 1.82. So, now for 0.55 we can find out the inductance, it comes the boost inductor 89.73 microhenry and for duty cycle 0.95 the boost inductor comes 7.64 microhenry. So, to ensure CCM, the value of inductor should be 1 millihenry and the output capacitor from this voltage ripple it comes 4.2, putting the value here it comes 4.27 millifarad. Coming to the example next one, design a single phase power factor correct bridge boost converter in boundary condition mode with a high frequency transformer operating 50 current with a specification of 120 volt 50 hertz and single phase AC supply of 230 volt and output power 1.5 kilowatt with output ripple of 2%. So, output voltage 2% ripple will be 230 multiplied 0 2. So, it will be 4.6 volt with power of 1500 watt. So, we have a nominal output voltage of 230 volt and the input voltage of 120 volt. So, rectified output will be 0.9 times 120, it is 108. So, output current will be P upon V 0, it is 6.52 and input current P 0 Vi and it comes 13.89. Output voltage relation in the turns ratio and input voltage relation. So, keeping a duty cycle typically in the range of 0.55 to 0.95 and taking a 0.95 duty cycle. So, putting the value we get the turns ratio of 0.21 and turns ratio for 0.955 duty cycle we get 1.91. So, we can find out for minimum inductance for duty cycle 0.55 it comes 19.57 and minimum inductance for D equal to 0.95 it comes 19.45. So, to ensure the BCM boundary condition we take the L minimum 19.45 and the output capacitor from this current ripple is 2, putting the value in this relation it comes 2.25 millifarad. So, with this we would like to summarize this the major shortcoming of the conventional AC/DC converter like high current and voltage distortion, low efficiency and heavy AC/DC filters are resolved by employing the improved power quality converters, and improved power quality converter is classified based on the type of power converter topology, nature of supply system and control of power circuitry. Further, a comprehensive analysis of various control algorithm of IPQC are presented here, and the operational analysis of various type of single phase unidirectional, bidirectional boost converter, improved power quality converter are discussed with their design process. A number of practical examples of boost improved power quality converters are given with the view of proper design exposure while considering the improved power quality performance. These are the references, and thank you.